So OSPF stands for Open Shortest Path First. This is a linked state routing protocol, and it maintains three different kind of tables: neighbor table, database table, we call this one also topology table, and routing table. Let's say we have few routers, router 1, router 2, router 3, like that. So you have R1, R2, then we have R3, and we may have another router R4. And they're connected in this way. Let's say R1 to R2, R2 to R3, R1 to R3, then R3 to R4. So OSPF is a dynamic routing protocol. So when you configure OSPF will check each of the link. So this is called link state protocol. So OSPF is one of the link state protocol. Its administrative distance is 110. Now OSPF calculate the matrix. Matrix calculation formula is cost. It is 110. Matrix equal to cost. Matrix, what is the cost? Cost equal to 100 or whatever highest bandwidth we have. So the link bandwidth, I'll just type link bandwidth divided by the highest bandwidth in the network. Highest, or we call it reference bandwidth actually. So let's say in particular R1 to R2, we have link bandwidth is 1000 MB speed, and highest bandwidth in the network we have 1000. So cost will be 1. In this way, OSPF calculate the cost. Link bandwidth divided by the highest bandwidth in this area. That's how OSPF calculate the cost. OSPF is a link state protocol. It checks each of the link, and based on that, it will send the traffic. Let's say this link cost is 100 MB, and this link cost is 1000 MB. So 1000 MB is faster than 100 MB, and this one is also 1000. So even though R1 and R3, they are directly connected, but this link speed is slow. That's why from R1 to, so traffic will go to R1, then R2, then the traffic will go to R3. In this way, traffic will go. So because OSPF is a link state protocol, so traffic will go via R1, R2, R3, because this is faster. Maybe this one we put some 100 meg link. Okay, so in this way, OSPF calculate the link path. After that, if you have multiple link, they calculate each of the link cost, and then after that, lower the cost, it will send the traffic via that way. Now OSPF maintain three different kind of table: neighbor table, database table, and routing table. Okay. Now, what is neighbor table? So R1 and R2, when you configure OSPF, they send in OSPF, each router, they send hello message to the other router. Hello, every 10 seconds, they send a hello message, and there's a date timer that is called 40 seconds. So in OSPF, each of the router, they communicate with other router in the network, like whatever directly connected. So they send hello message. Hello, every 10 seconds, they send a hello. Other one should reply back. If somehow other one not replying back within 40 seconds, then it's considered that neighbor is dead link. So in this way, OSPF check each of the neighbor routers. And also OSPF, one of the important things called router ID. So what is a router ID? Router ID is the ID number for the router. Let's say we write down in this way 1.1.1.1. It's similar to IP address. In this format we write down router ID. So router ID is kind of like a ID number for the router. In OSPF, every router we should have router ID. So this is a configurable value. That means we'll be able to configure that one. So neighbor relationship is maintained. So R1 neighbor is R2, R1 neighbor is R3, etc. But R3 neighbor is R1, R2, and R4, all of them. After that, OSPF maintains database table. Database table means inside the area, all the router information will be like router database. Let's say we need to have an area. What is the area? Area is kind of like a boundary. In OSPF, every router must be part of a boundary. So this is called area. First area will be always area 0. This is also called backbone area. Area is kind of like a boundary. So in this boundary, we have 3 routers. So if you looked at R1 database, you'll be able to see these 3 routers informations. Whether you're looking at R1, R2, or R3, you'll be able to see this area. We have 3 routers. So all of the routers informations you'll be able to see part of the database table. We have another area, let's say R3 to R4. So basically, this is area 1. And this is area 0, and that is area 1. So area 1 is another additional area. So area 1, we have kind of like router 3. Router 3 will be part of same area. Router 3 and router 4. Router 3 is kind of like a common. Common is part of like area 0. Also, it will be part of area 1. Because router 3, one interface or couple of interface in area 0 and another interface in area 1. So in this way, we actually have 2 area. So once you have a 2 area, so database sections will be separate. That means for this area 1, we have R3 and R4, these 2 routers database. So basically, it will be kind of, yeah, R3 kind of like part of both areas. So R3 kind of part of both areas. Area 1. So database table related with the area. So in this area, we have 3 routers, and area 1, we have 2 routers. And router 3 is part of both areas. That's why router 3, we call it ABR router. ABR means area border router. We call it ABR. Area border router. So we have neighbor table, database table, and routing table. What is a routing table? A routing table will have the best path, like whether from R1 point of view, whether you're sending via R2 or sending via R3. So which way you're sending the traffic. So basically, that will be depends on this routing table. So routing table will have a best path. So this is the informations we have around OSPF. Let's have a look from our slide. So OSPF stands for Open Shortest Path First, and OSPF is a link state protocol. So it's basically it checks the link, and OSPF maintain these 3 different kind of table: neighbor table, database table, and routing table. Now, how OSPF neighbor table built up? Let's have a look. At first, router determine the router ID and add interfaces to the link state database. Router ID is that 1.1.1.1, those kind of ID number it will add, and then add that interface to the link state database. After that, it will send a hello message. Send a hello message on chosen interface. This is called down state. After that, other router receives the hello. This is called initial state. And then router sends a reply to hello. This is called two-way state. After that, master-slave relationship determined. This is called external state. Then database descriptions are acknowledged and reviewed. This is called loading state.
Sorry, what is step 6?
Step 6 is a master-slave relationship established. That means one of the router will be master and another router is basically asking the database update or database informations. So let's say router 1 knows all the other router informations. So it will be automatically selected as master. And the other router, it is actually asking the informations that will be like slave router. In this way, one router will be in master state and the other router will be slave state. In this way, slave will update the routing table from the master table.
Okay, thank you.
Yep. After that, the database description. Database description means, like, let's say R1 knows something about R2 or R3, those informations. So those informations it will send to the other router. So that another router will acknowledge and review. That means kind of they already exchanged their database informations. And number 8, after loading state, like neighbors are fully synchronized. That is called full state. That means both router has been exchanged the hello message, exchanged the database descriptions, and pretty much they are up to date. So that's how we can say that OSPF is functioning in this level properly. So when you initially configure the router, that time, these are the steps it actually follows. Now, router determine the router ID. So router ID is the name of the router in OSPF. It identifies the router to OSPF neighbors. And router ID must be unique. And router ID selection, it is the highest physical interface at startup. So basically, it is the highest physical interface at startup. Loopback interface bit physical. Router ID command bit all. So router ID command means is basically it will block all the router ID command. It will actually bit all. That means if you configure router ID, that is the best practice. In this way, you know that what is your router ID. But if you do not configure, your router will try to find out any loopback address. Loopback address is another testing purposes. Sometimes we configuring inside our router. So if we have any loopback address, then router may select that one as router ID. But if we do not have loopback address, then router will try to find out highest IP address in the router. So if router found that, then it will select that one as a router ID. But this is like automatic selection. So, but best practice, just simply configure your router ID. If you configure, then you know what is your router ID number. Now, this is R1 and R2. So R1 and R2 links come up and it's sending a hello message. This is a router ID. It is sending a hello message, and other router also understand the hello message, so it will reply back with a hello. So with a hello message, basically they exchange the router ID informations. And this is the two-way message. So let's say this is 1.1.1.1. 2.2.2.2, basically it will exchange those router ID, and this is called two-way state. After that, R1 and R2, they actually exchange the database informations. So part of that, we have database descriptions. Let's say R1 send database informations to R2, and R2 will send the database informations to R1, and then loading state, link state update with several LSA. So basically, several LSA will be updated. Maintaining neighbors and the LSDP. Maintain neighbor state by sending hello message based on the hello interval 10 seconds and listening for hellos before the date interval 40 seconds expires. So hello and date interval must be same in order to form OSPF neighbor relationship. So basically, OSPF router, they'll send receive hello message. So basically, they will send hello every 10 seconds and date timer is 40 seconds. But in order to make the neighbor relationship, both router hello and date interval must match. They need to be same. Remember this one. Now flood any changed LSAs to each other, each neighbor, and reflood unchanged LSAs to their as their lifetime expires. Default is 30 minutes. So basically, so they will exchange the LSA. And after that, if any changes happen, it will flood that information to neighbor. But if nothing happen, every 30 minutes it will provide the informations to other routers. Because every 30 minutes, that kind of whatever, if nothing happen, every 30 minutes they actually update this link state advertisement informations. So how to calculate the routing path in OSPF. So OSPF calculate the cost. So cost equal to 100 divided by bandwidth. So this is the formula. So basically, if it is a 56 KB speed, so 100 divided by that link bandwidth, and you'll get the cost like 1785. Then 65,000, you can see cost is very high, 1562. T1 link cost is 65, Ethernet 10, fast Ethernet 1. So in this way, the OSPF calculate the cost. So let's say R1, R5, R6, R8. So let's say R2, R3, R4. So you can see the cost. So R1 to R5 cost is 20, this is 30 and 40. So this way cost is 90. And if you send the traffic via this way, cost is 30, 60, 20, and 5 is 115. But this side, if you send the traffic, cost will be 10 plus 180. So that's basically 190. Right? So middle one has the better cost. So middle one cost will be 90. Now OSPF areas, scale OSPF using area, basic rules. Put all interfaces connected to the same subnet inside the same area. So routers internal to an area with all interfaces assigned to that single area. So routers may be ABRs. ABRs means area border routers. We talk about the area, right? Area means a boundary basically. So some interfaces connected to the backbone area. So what is a backbone area? Area 0. First area, which is area 0, that is the backbone area. And all other area, any other additional area, we call them non-backbone areas. Now all non-backbone areas must connect to the backbone area. Now OSPF area design advantages. The smaller per area, LSDP requires less memory. So routers require fewer CPU cycles to process the smaller per area LSDP with the shortest path first algorithm, reducing CPU overhead and improving convergence time. Reduce number of routers to rerun the shortest path first algorithm. And reduce bandwidth. So less information must be advertised between areas, reducing the bandwidth required to send LSS. Smaller the area, let's say in one area, if you have 20 routers, so you'll have a lot of broadcasting. But if you divide those 20 routers in, let's say, area 0, you put 10 routers, area 1, you put 10 routers. Then in this way, we can divide them into different areas. So if you divide them, then we'll have a smaller area. And in this way, router performance will be better because router has to do less calculations. When if routers want to find out any subnet or traffic, it will take less time. So by default, even if you don't have anything, you must have to have a one area that is called area 0. After that, if you have a large network, maybe you can create additional areas such as area 1, area 2, like that. But first area will be always area 0. Now OSPF using these concepts called designated and backup designated router. Based on the network type, OSPF router can elect one router to be a designated router and one router to be a backup designated router. DR and BDR serves as the central point for exchanging OSPF routing informations. So basically, in routing environment, one of the router will be designated router. So that router will be responsible for exchanging all these database informations. And if in case this router failed, another router will work as like a DR router, that is called BDR, backup designated router. All these DR, BDR router, they communicate inside the OSPF environment with this multicast address called 224.0.0.6, or they update via 224.0.0.5. These two multicast address, they actually reserved for this OSPF internal communications. Now, how to select the DR and BDR router? So a router who has highest priority, that router will be the DR. But by default, all the router priority is same, 1. That's the default priority, that is 1. But if all the priority they are same, router who has highest router ID, that router will be the DR router. So let's say you have R1, R2, and R3. In here, see, assume that all the router has the same priority 1, default priority. We can change the priority. In this way, we can make a router as a DR router. But in these 3 routers, see, the router 3 has the highest router ID in here. So it will be the DR in this case. DR means designated router. So this router will be responsible for exchanging the database informations. Let's say inside many database, let's say all the router, they will exchange their database informations with the DR router. But if you have a large network, you can have another router and can work that one as backup designated router. So basically, in this case, maybe R3 and R4, if this one has a highest router ID, this one will be the DR router. But this is configurable value. We can configure. Let's say if we do not want that, if we do not want to do that, we want to make this one as a DR router. This interface, we can change the priority. And we can make priority, let's say 100. So that's it, then it will be DR router. So this part we can actually configure. But DR router will be responsible for exchanging the updates with the other routers. OSPF, so basically OSPF packet types, you have a hello packets. Part of that we have database descriptions. Then we have link state request, which is LSR. Part of that we have slave or master request. Then link state update, which is LSU, reply of the link state request. Okay. These are the message types, like OSPF router, they communicate, they update something, they acknowledge something, they advertise something. So link state advertisement, we call it LSA, updates about the individual route. LSU will have one or more LSS, and link state acknowledgement, which is LSAC. OSPF is reliable, basically. Now we have subnet mask and wildcard mask. Let's say in subnet mask, 32 bits. Subnet mask is 32 bits, and wildcard mask is also 32 bits. Subnet mask we write down in this format, and wildcard mask we write down in this format. And then subnet mask, if 0 bits, we call it host, and it's important for the wildcard mask. But 1 bits, this is called network bit, and wildcard mask, we call it ignore bit. This is exactly same as access control list we have looked at yesterday. Basically, they're using this 0 and 255, these two values. So if you say 10.0.0.0 wildcard mask, if you put 0.255, so that means it will allow 10.0.0.0 network. It will allow 10.0.0.0 network. And 10.1.00 is like 00.255. We allow 10.1.00 network. Then we have 10.1.1.0, then 0.0.0.255 allow 10.1.1.0 network. Like 10.1.1.1, and this is the wildcard mask 0.0.0.0, allow the host 10.1.1.1. So basically, in this way, we put the wildcard mask, and when you configure OSPF and this subnet, they work in this way. Now, configuration part, OSPF configurations, we have, let's say, router 1, router 2, and router 3. And these 3 router, we want to configure R1 to R2 OSPF. So we can say, first of all, each of the interface we need to configure. And then we can say router OSPF 1 is a process. And then we can enable router ID, say router ID 1.1.1.1. And the network, we need to add this one, 11.1.1.0. So network, we add that subnet, wildcard mask 0.0.0.255, area 0. So all of the routers, they will be part of area 0. Then we go to R2, say router OSPF 1, then router ID 2.2.2.2, network 11.1.1.0, and then 0.0.0.255, area 0. Then network 12.1.1.0, and the wildcard mask, because this is /24 network, that's why wildcard mask will be 0.0.0.255, area 0. You can see these two subnet, they are part of area 0. Then we move to router 3, router OSPF 1. You can see the process will be same for all of the routers, and router ID, we put 3.3.3.3, and we add this subnet with a wildcard mask. Say network 12.1.1.0, 0.0.0.255, area 0. So in this way, we configure each of the route. Once we configure, then routing will be enabled. After that, we can send the traffic to R1, and traffic will travel via R2 and R3. In this way, it will go to destinations network. Now we can apply some show command. Let's say show IP OSPF, show IP OSPF neighbor. So with that, we can check the neighbor informations. Show IP OSPF database. We can check the database informations to check the entire database for an area. Show command, with that we can actually verify all the configurations and all these other informations as well. Show IP OSPF interface. Check the OSPF interface for hello and date interval. Show IP protocol. Show you the number of protocol and details. Show IP route. Show you the routing path. and then clear IP OSPF process with that command. This command is required, let's say, if you change the router ID. To update that router ID, we can refresh the process. So only that time this is important. Otherwise, we do not apply this command. In case if you have multiple areas, let's say in this topology we have area 0 and area 1. So this kind of scenario, when you configure this router, like router 1, say router OSPF 1, router ID 1.1.1.1, network 10.1.1.0, and then 0.0.0.255 area 0. So you can see that you add this subnet with area 0. But when you configure router 2, you can add the router ID and then add the network. But for this network, you put area 0. For this network, area 1. So that's the only difference. So because this router is connected with both areas, so we just need to add the related subnet with the relevant areas. And then router 3, say router OSPF 1, router ID 3.1.1.1, and you add the network 11.1.1.0, and then 0.0.0.255 area 1. Another things we have, this is one of the features called passive interface. So sometimes some of the OSPF router, some interface may be not connecting with any of the device, or maybe it's connected but is not participating in OSPF process. That kind of scenario, we do not want to send any hello message from that particular interface. And then we make that interface as a passive. Passive means it will not send any hello interface. It will not receive any hello on that interface, and it will not make any neighbor relationships with the other interface. Passive means it is not active. We want to make it kind of passive. So how to configure that? We can say passive interface and put particular interface, let's say fast Ethernet 00. So this interface will be passive. And if you say passive interface default, basically all the interface will be passive then. So these are the stuffs we have in these sections.